Hi everybody, welcome to lecture 20 of Electrical Engineering 331. In this lecture we're going to consider some applications of the Laplace transform. So the first application we will consider is circuit analysis basically. And I know that you do circuit analysis of some rather complicated circuits in 360. In this course, it's not our goal to try to analyze extremely complicated circuits, but on the other hand, we would like to look at a few circuits to help illustrate how useful Laplace transforms can be in analyzing them. So you see that in this first circuit here, we have a resistor and a capacitor and an inductor, and Vs of t is our source, and the voltage across the capacitor we've defined as Vc of t. The voltage, at least initially here, across the inductor is defined as V out of t. The current through the inductor is I sub L of t. And our goal here is to find V out of t for a particular Vs of t. Maybe rather than particular, I should say arbitrary, because the idea is that for what we would like to do is to get an easy way to find V out of t for any Vs of t, so that we don't have to go and reanalyze the circuit each time, but can have something that's very convenient to work with. So the let's see how this will go. In fact, actually, I guess, let me just, hate to be picky, but let me change this word particular to arbitrary. Well, after thinking about it, I decided I didn't like arbitrary either. I said given. So want to find V out of t for a given Vs of t. I think that that's pretty clear. Okay, so the voltage across the capacitor, in case you're a little bit rusty with this, it's equal to Q over C, basically, where Q is the charge across the capacitor and C is the capacitance. And Q is the integral over all time of IL of tau in this case. Notice that IL is the current that's flowing down here, but that's the current everywhere in this problem. And so that's why we have IL in here. So again, Vc of t is 1 over c times the integral of all time of IL of tau d tau. And on the other hand, V out is L dIL dt. Now I'll go ahead and tell you that in the test, in test 20, we're going to look at this problem with V out defined as the voltage across the inductor and a couple of problems, but we'll also look at it with the V out defined as the voltage across the capacitor or the voltage across the resistor. In each case, it's the same circuit, but we're just defining V out in different ways in some of the different problems. Okay, so our circuit equation then is going around the loop here. We have Vs of t plus Vs of t minus R IL of t minus Vc of t minus V out. And now we're back to where we started, so that's equal to 0. That's just Kirchhoff's voltage law. And so when we substitute in these expressions here for Vc of t and V out of t into that equation, then we get this equation down here, Vs of t minus R IL of t minus 1 over c and notice that I've broken the integral up. Up here I have the integral from negative infinity to t, but I've just broken that up into two pieces. I have an integral from 0 minus to t and the integral from minus infinity to 0 minus. The reason that I'm doing that is that we have the Laplace transform for this expression, but we don't have the Laplace transform for this expression. So that's the reason for breaking this up. And then the v out of t, as we said right here, that's equal to L dIL dt, so I have substituted that right here. Now, before I go any further, I want to make sure that one thing is clear here. Notice that this minus L dIL dt, again, that's minus v out. In this case, where we have defined V out as the voltage across the inductor. But in the problem where we've defined V out as the voltage across the capacitor, then V out will be, minus V out will be this term. Okay? And when we define V out to be the voltage across the resistor, then this will be minus V out. Okay? So the equation here for the circuit will be the same in all three cases, but this V out of t will have different expressions in each case. In problems 1 and 2, V out is equal to this because it's the voltage across the inductor. And in problem 3, V out will be equal to this because it's the voltage across the capacitor. And then in problem 4, V out will be equal to this because there is defined as the voltage across the resistor. Okay, so now that we have said a little bit about that, let's go ahead and proceed. In going from this line right here to this line, all that I have done, the only thing that I've changed is right here. And what I'm just observing here, that if we integrate the current flowing into the capacitor over all time up to 0 minus, then what we get is the total charge on the capacitor, across the capacitor at time 0 minus. So that's why we can substitute QC of 0 minus for this integral. And QC of 0 minus will be some constant. Okay, now as I go from this line to this line, I have made one more change. Notice that I've gone ahead and multiplied through by 1 over c for everything in this term. So I have minus 1 over c, integral of 0 minus to t of IL of tau d tau, and then minus QC of 0 minus over c. But everything else is the same. Now, we're about to take the Laplace transform of this, and if you look in your table, you don't have any entry for taking the Laplace transform of a constant. This is a constant here. But remember that it really represents what's going on. It's only constant, in other words, from 0 minus to infinity. It's not going to be constant. This QC is changing. QC of 0 minus, it's not even really defined if t is before 0 minus. So the point here that I'm making is simply that you should think of this as being QC of 0 minus over c times u of t. And furthermore, this Q, the charge on the capacitor divided by the capacitance is the voltage. So really you can think of this as VC of 0 minus. In other words, that's the initial voltage across the capacitor just before t equals 0. And then we multiply that by u of t, because that will be equal to that for all time. You know, the VC is a constant, so that's why we're multiplying it by u of t, which is constant and equal to 1 for t greater than 0. Okay, so if we will simply think of that as being equal to this, then we can proceed with this problem pretty easily. Let's go ahead then and take the Laplace transform of everything that we see here in this equation. And when we do, then we get Vs of s is the Laplace transform of that. Now r is a constant, so we don't have to worry about it. But the Laplace transform of IL of t will be capital IL of s, and then here we'll have a minus 1 over c, and then the Laplace transform of the integral from 0 minus to t of IL of tau d tau is IL of s over s. And then here, since this term is Vc of 0 minus times u of t, we know that the Laplace transform of u of t is 1 over s. So this just becomes minus Vc of 0 minus over s. And then finally, we take the Laplace transform of this, and we know that so the minus L can come out, and the Laplace transform of the derivative, you can look this up in your table, it's s times the Laplace transform of the function itself minus the value of that function at 0 minus. And then this whole thing is equal to 0. So in this problem, we have, or in this equation, we have two initial conditions. We have Vc of 0 minus, which is the voltage across the plates of the capacitor at the time just before 0. And then we also have IL of 0 minus, which is the current flowing through the inductor just before t equals 0. Okay, so having observed that, we can go to the next line, and here I have simply gathered together all of the terms multiplying the Laplace transform of IL. And by doing that, I have also really gathered together the two initial condition terms. And notice that they sort of naturally fall in with the source as well. Okay, so then what I will do is take all this stuff dealing with IL, I'll take it over to the other side of the equation and then divide by the coefficient of IL. And so I end up getting this equation that you see right here. IL of s is equal to, okay, we have the Laplace transform of the source minus this initial condition term for the capacitor, and then the initial condition term for the inductor, and then divided by R plus 1 over Cs plus Ls. And now recall that our goal here was to find V out of t very easily. And in this particular problem, V out is equal to L dIL dt. So if we take the Laplace transform of that, we get V out of s is equal to L times S IL of s minus little I, that should be minus little IL of 0 minus. So let me just stop and put that L in there. Okay, so now we have that IL in there. So V out is equal to that when we take the Laplace transform of this equation, which we already have discussed above. And so then if we simply substitute into this equation for V out of s, if we substitute what we derived up here for IL of s, we will get this. So here is our equation for V out of s. And notice that if you know the parameters, if you know the values of the elements in the circuit, then it's really pretty easy now to find V out of t. Because if you know L and C and R, and then for whatever source, just take the Laplace transform of it, substitute it in there, and then you have the Laplace transform of the output, and you can invert it and find V out of t. Now, what we will do in the remainder of this problem and in all of our test problems, 1 through 4 at least, we will assume that the initial conditions are 0. Now, in problem 5, which doesn't deal with a circuit, it deals with a coupled pair of differential equations. In that problem, the initial conditions are not 0. But in problems 1 through 4 on the test, the initial conditions will be 0. And you'll see now that if the initial conditions are 0, it really makes this expression here significantly simpler, because this last term will drop out, and then this term up here will drop out, and this term will drop out, and so we're just left with Ls times Vs of S divided by R plus 1 over Cs plus Ls. So that gives us V out of S in terms of Vs of S. And notice that here, to get this expression, I've simply, of course, taken the Vs of S over here, and I've decided to go ahead and multiply top and bottom by S so that we wouldn't have this 1 over S here in the denominator. Okay, so now, as I say, all you have to do is that for any source that you have, just take its Laplace transform, plug it in there, multiply by that, and then take the inverse Laplace transform, and you'll get V out of t. So for instance, if we let Vs of t equal delta of t, remember the Laplace transform of delta of t is just 1, so in that case V out of S will be equal to this. So as I say here, we could easily find V out of t, which would be h of t in this case. Because why would V out of t be h of t? Because it's the impulse response. We're looking at what the output is when the input, Vs, is equal to the impulse. So actually this would be h of S for this circuit. This would be the Laplace transform of the impulse response of that circuit. But as we've said, we can also find the output for any input, as long as it has a Laplace transform. So we'll see some examples of this in problems 1 through 4 on the test. And then we'll do one more example here in this lecture, and this example will help you understand how to do problem 5 on the test. And this is really pretty easy, but it's interesting to learn about. So sometimes in the analysis of some problems, you will come up with what's called a coupled pair of differential equations. And what that means is that, for instance, for these two equations, you have x and y are sort of tangled up together. You can see that both equations here involve x and y, and there's no clear way to get one equation with x alone and another equation with y alone. It just doesn't seem quite possible as long as you have these equations in the time domain. But, or at least let's say it would be very difficult. But if we go to the Laplace domain, we'll see that it's easy to solve this system of coupled differential equations. And by the way, these two equations have these initial conditions. We have an initial value for x, and we also have an initial value for y. Okay, so what we're going to do is, as I said, in order to solve this this system of equations, we're going to take the Laplace transform of each equation and see if we can work in the Laplace domain or the S domain more easily than we can in the T domain. So when you take the Laplace transform of the derivative, you again look at your table and you can see that the Laplace transform of a derivative is S times the Laplace transform of the function minus the function itself evaluated at 0 minus. So that's going to apply both in the first equation when we take the derivative of x and, when we take the Laplace transform of the derivative of x, and it's also going to be applicable in the second equation when we take the Laplace transform of the derivative of y. So you can see that these first two terms here are just like the first two terms up here, except we have y instead of x. And then the rest of this is pretty straightforward. The Laplace transform of 3x of t is 3x of s. Laplace transform of 8y of t is 8y of s. The Laplace transform of 3y of t is 3y of s. And the Laplace transform of negative 2x of t is negative 2x of s. Okay, so now what we will do is use this information about the initial values of x and y. We will use that and plug those values into these two equations, and we'll get this. And notice that in these two equations, I have now dropped the argument of s everywhere just so that it's easier to write. But you should remember down here that capital X and capital Y represent Laplace transforms. Okay, so now that we get these two equations in this this form, let's try to simplify them a little bit more. What we'll do with the first equation is we'll group together all the terms involving x. So you have s plus 3 times x, and then minus 1 plus 8y is equal to 0. And in the second equation, we'll group together everything that has y. So we'll have s plus 3 times y minus 2x is equal to 0. Now, you were asked in this problem to find x of t. So since we were asked to find x of t, the way that I will proceed is to solve this second equation for y and then substitute what I have into the first equation so that I get equation in x alone, and then I can invert that to get little x of t. But on the other hand, if I had been asked for y of t, then my approach would have been to solve the first equation for x, and then whatever I obtained to substitute that in down here. So, I mean, it's not, this is not any big mystery. I mean, it's going to work out, even for instance, if you had solved the second equation for x and plugged in there, or solved the first equation for y and plug in there, that will work fine too. It's just however you want to do it. But the point is that once we take the Laplace transform of these differential equations, then we get two equations in the S domain that are easy to work with. So again, what I've decided to do here is solve the second equation for y, and when I do that, I get this, and then I take that value for y, plug it in there, and so you can see I have s plus 3 times x minus 1 plus 8 times y becomes 8 times this quantity here, 2x plus 2 over s plus 3. Okay. Now, the analysis of this equation turns out to be particularly nice. What I've done here, I multiplied through by s plus 3. So this became s plus 3 squared. The minus 1 became minus s plus 3. And the 8 times 2x plus 2 over s plus 3 just becomes 8 times 2x plus 2. And then I was about to multiply this all out, but began to look at it more closely and realized, oh, wait, it looks like some nice things are happening. So instead of multiplying everything all out, I just left it pretty much as it was. So that here's the s plus 3 squared times x. Here's s plus 3 squared times x. And then over here we have a 16x. And so I wrote that right there. And then I wrote down the minus s plus 3. And then notice we also have a 8 times 2, so that's plus 16. And so then I left this term involving x on the left-hand side of the equation, but I brought these two terms over to the other side. So the minus s plus 3, when it comes over to the other side, becomes positive s plus 3, and the positive 16, when it goes to the other side, becomes negative 16. And now I go ahead, in order to solve for x, I divide both sides of the equation by s plus 3 squared plus 16, which is the same thing, of course, as s plus 3 squared plus 4 squared. And so I have s plus 3 divided by s plus 3 squared plus 4 squared. And then I'm going to rewrite 16 as minus 4 times 4. And then I have s plus 3 squared plus 4 squared. And this is just perfect because, as you probably recognize by now, this is the Laplace transform of e to the minus 3t cosine 4t u of t. And this part right here is the Laplace transform of e to the minus 3t sine 4t u of t. And then that's getting multiplied by negative 4. So our final answer, after we take e to the minus 3t out of both terms, is e to the minus 3t times the quantity cosine 4t minus 4 sine 4t, all times u of t. And so that's an example of how we can use Laplace transforms to solve systems of coupled differential equations, which can indeed be very handy sometimes. So that concludes lecture 20, and I think that should get you prepared to work on test 20. So good luck.